Hello everyone, welcome to Stochastic Calculus for Finance 1. This is section 5.2 on the first passage of time, and we're on the second part here. So in our previous video, we gave the definition of what we mean by the first passage of time, and this was the definition. And in particularly, we raised three interesting properties that we were trying to prove. And we will start actually the proof of this property here, which tells you like if I pick a level m, then sooner or later, I know that symmetric random walk, this guy here, Mn, sooner or later will reach this level M with a probability of 1. And that's the proof that we started and that we will continue here. So again, what we want to show exactly is this property here. And what we did in the last video is show that this stochastic process defined by this expression is actually a martingale. Now, before going any way further, I want to take some time to really show the big picture. Because in chapter, it might look really strange, like, okay, we want to show this, then why do we care about this seemingly very random stochastic process that we're coming out of nowhere? Well, I think I will show you the big picture and show you how we can use really these guys really at the end of the day to show this property. So what the game plan is, this is the map of our game plan of our proof. So first, we're going to take some time and actually show that this property here is true. And what this is saying is that the expected value of the stochastic process that we define here, stop it at the stopping time, tau m, is actually equal to 1. The expected value is equal to 1. And after showing that, we will show a second property as well. And on this one, we show that the limit as n goes to infinity, right, of the stop it process here is actually equal to this expression. And again, this might look real random, but what we will find, and we'll show is that actually once we have these two properties in our belt, then it's very easy from there to show that this final part, the property that we're going to show at the end of the day, is true. So let's go on and now focus on this part and show that this thing is actually true. So we have seen before that the martingale that is stopped at the stopping time is also a martingale, right? And so we have shown this process Sn is a martingale. So the process Sn stop at the stopping time is also a martingale. And what this allows us to do is then we can write this expression here. And we can write this because we know this is a martingale, right? So that means the expected value of, and by the martingale, so what we can write is basically S0 to M, right, is equal to the expected value of the stochastic process at any time other in the future as we're seeing it today, right? So S0, Sn tau m. And because this is the minimum between time 0 and time tau m, so I don't care what time m is going to be, right? Because time is going from 0 to plus infinity. Then the minimum here is definitely going to be 0, right? So we can just simplify by just writing S0 here. And that's exactly what we did here. So now we have written this. What this will allow us to do is then to write, okay, so what is exactly this S0? So I just need to see everything I see on n in this expression up here. Everywhere I see an n, simply replaced by a 0. Simply replaced by a 0. And that's what we show in the next here. So the expression is given by this. And something to the power 0 is definitely 1. Something to the power 0 is also 1. And just in case you wonder where the 0 is coming from, well, m0, what is this exactly? This is like basically the value of the symmetric random walk at time 0. And by definition, the symmetric random walk is starting at 0. So that means this m0 is actually equal to 0. That's why we replace that here. So if you really think about these concepts, they are not that mysterious. So we can really write now that this guy hold, right? And this is one of the first properties in our map that we want to be able to show. And this is true for all n greater than or equal to 0. So in our previous slide, we successfully managed to show this expression. So let's now move to the second part, where we're trying to find the limit as n time tends to plus infinity of this frozen / stopped process at time tau m. So let's show the second part. So let's consider basically this limit when n tends to plus infinity of the stopping process Sn We have shown before that Sn is we have defined the stochastic process Sn here. So to get Sn to m, the stopping process, every time we see n here, we just replace it by n and to m, and that's exactly what we did here. We saw n here, so we replaced it by n to m. We saw n here, we replaced by this guy. Very simple stuff. So now we consider this, and we want to find the limit when n tends to plus infinity of this whole thing. So what we can do is first analyze what is the limit when n tends to plus infinity of this first term here. Then look at what is the limit when n tends to n. What can we say about when n tends to infinity of the second term here? And maybe if we know enough about these two terms, then we can say something about the limit of the whole thing. So that's our game plan here. So first we try to figure out what is the limit when n tends to infinity of the let's say the first term first before. So we want to know this limit. So we're gonna start looking at the first term first, and the first term is essentially this guy here, all right? So well, if we notice something that this term is actually bounded by this property here, by 0 and e power sigma m. So why is that? Well, the first part is easy, right? So the exponential is strictly a positive function. So e to the power whatever, I don't care, is going to be greater than or equal to 0. So the first half here, this guy here is very easy. So let's now look at the second part here. Well, to figure out this, we know also the exponential is an increasing function. So we can just focus really on figure out what is the relationship between these two. Well, and for that, we can really show something. So we have sigma on both sides, so maybe we can ignore the sigmas. So the thing we need to really spend some time focusing on is this expression. We need to show that this is less than equal to m. And if it, by definition, this is true, right? Because this is the symmetric random walk that stopped at stopping time to m, right? So graphically, this is exactly what it means. So let's say we have time on our axis here, and this is basically the value of our random walk. So, and we have like a level m that we pick here, right? So the symmetric random walk, naturally we start at 0, and we'll do what a random walk does. It's going to go randomly down, up, right? And exactly what this tau m is at this level tau m, that is the very first time that this process, this frozen process is reaching level m. And when it reaches level m, the stopped process or this frozen process is going to does what stopped process does, or frozen process is going to be frozen at this level here, going on at m forever. So no matter what, wherever I look, no matter where I look on this, in this area here is less than m. After that, it's equal to m. So this relationship hold. So that means like if I take the exponential of this, then again, this relationship is going to hold. Nothing very, very mysterious there. And remember, we said sigma is actually a positive number, so this relationship is going to hold. So that's like something we can notice first, and we know it's true. Then we can move to something to the second term. Actually, try to understand the second term. Well, focusing on the second term on this guy, what can you say about this when actually n is going to plus infinity? Well, essentially we can say this. Basically, if tau m is anything but infinity, then this is the result. We can get the value by this. And if tau m is actually the stopping time actually plus infinity, then we get 0. Well, let's dig deeper and try to see if we can understand that. So if you remember well, this notation n tau m is nothing but the minimum, right? The minimum between n and tau m. So having this, then we can, okay, so if tau m is less than infinity, right? Tau m is less than infinity, but n is actually tending toward infinity, so n is going to be larger. So that means like the minimum between n and tau m in this case is going to be tau m. So that means as a numerator here, we need to have only one thing, tau m. And that's because we took we took the case where there is no n anywhere anymore, so we can forget about this. So this is basically the value, and that's exactly what we have here. All right, so this guy is this first one we verify check. So let's say that what if like instead that this tau m is actually infinity. Well, if tau m here is infinity, and this guy is only trying to get to infinity, it's just tending to infinity, then the minimum is definitely going to be n, right? So that means the result can be written as 2 divided by e sigma, which is a constant that's positive, e minus sigma naturally is negative, uh, exponential, and n is actually going to infinity, right? So we can write this as a function. Let's say x, this is a function x, and say y is equal to this. So we want to find this value when x is getting really big, tending to infinity, right? So that's essentially what we're trying to find here. And I'm putting it this way because to find the result, to find the zero, we can actually do some complicated mathematics to try to find this, or we can just plot this function and look how this function is behaving. I find that a little bit easier sometimes and a lot more intuitive to show that there is no weird, complicated mathematics going on in the background to find this relationship. So, and when you plot this curve, and there are like many different solutions you can use to plot that. So this is what I did exactly. I plotted it, and this is the x, which is whatever is going here, and I'm saying that is going to infinity. So what is the value of the function then? So I can see that when x is increasing to infinity, then the value of this function is actually very, very small, right? It tends to 0. That's where the 0 is coming from then. So knowing that, then we can really write this basically. The lim when n tends to plus infinity of, well, this is actually Sn tau m is equal to basically this first part here, right? And where this first part is coming from, what is this indicator function? This is just like something that tells you if tau m is less than infinity. If that is true, then this is the number, and that's exactly it. If it's not true, then that is 0. So that's why basically this indicator function is saying. So the indicator function here is just just a more compact way of representing whatever is here. And now where is this coming from? Well, this is actually the second term. When n is going to plus infinity, right, of this expression here, we're saying that is just basically if n is plus infinity, then it's going to be bounded, and it's bounded, and it's multiplied by 0, so we get 0, right? So 0 multiplied by whatever is 0, so this indicator function will help us with that case. But in the other case where actually tau m is less than infinity, but n is tending to plus infinity, right? So if tau m is tending to plus infinity, then the minimum between n and tau m is going to be tau m, right? And then we have m tau m. What is this m tau m? M tau m by definition is basically the time where it reached the level m for the first time. So the value of the symmetric random walk at that time is just m. So that's where this m is coming from. So this is like a more compact way of showing what the limit when n tends to plus infinity of this topic process, right, is given by this expression. All right, so I think that's okay. So that means that from there, then we managed to show the second part here. And we showed earlier this part here. So now we're going to combine these two to find basically to get to this thing. So let's combine these two and see what we get. Okay, so now what we can do is I'm putting this on the right here to compile everything we learned. And in particularly we're going to pick like, so far we have used a generic sigma. So we can pick a sigma that's infinitely small, or just say sigma is 0. And this has been working for basically any n, so we can pick also n that's really large, n plus infinity, right? So using our first property here, we know this is true, and for all n, it's always going to be true also for an n that's pretty large. And we did the hard work actually to finding what the limit of this is when n tends to plus infinity, right? That was the second property here. So that's what we're using here, and this was true for a generic sigma, right? So this is going to be true for a special sigma, which is the sigma I'm going to repeat here is just 0. And we say this whole thing is equal to 1. Naturally, this is just basically, we haven't changed anything. We're just still using this. So now we can do some basic computation. 2 divided by e to the power some 0, that's 1. E to the power minus 0, that's 1. So we have 2 divided by 2. So this whole thing is just going to be 1. And we have e to the power 0 multiplied by something, that's just 1. So at the end of the day, really what we have is just basically the expectation of the indicator function here. And by definition, basically the expectation of the indicator function, this indicator function indicates basically, are we in the event where tau m is less than infinity, right? And that's basically the probability of tau m is less than infinity. And we have shown that basically that this guy here, this thing here is just 1. So that we're done. We have just shown that basically the probability that this tau m is less than infinity is just 1. So sooner or later, if I pick a level m, I don't care what the level m is, the random walk is going to do whatever it wants, but I know for a fact that sooner or later it will hit this level m. That's what basically the first property is telling us, and that's just what we managed to show. So this is the end of this video. So next we will going to try to go through the second part, the second property. Thank you very much.